In the past, you might have actually dealt with magnetism and then electricity to be two separate things, but in reality, there's only one force, the electromagnetic force. In fact, all magnetic fields, all magnets are caused because of moving charges. Those two things really are the same. It is causal there. So let's actually talk, though, a little bit about what a magnetic field is. Anytime you see a field, it's just meaning an area in space. And in this magnetic field, any magnetic metal, if we were talking about specific metals, it has unpaired electrons there. It would experience a force, or another magnet could experience a force inside of that field. Now, magnetic field lines always go from north to south. So for this bar magnet, the magnetic field lines curl around on the outside from north to south. Now, on the inside of the magnet, it goes the other way, south to north. But it goes from magnetic field lines go from what would be considered a north pole to what would be considered a south pole. Likewise here, we bring a north pole near a south pole, where the lines would go from north to south. Also notice that in the very center here of this north and south pole, your lines end up becoming very close to parallel. So if we were to kind of zoom in here, we would end up having nice parallel lines for our magnetic field, but then it begins to bubble out on the outside. The density of the field lines, it gives you the strength. So the more lines you have, the greater the strength of the magnetic field. In magnetic field lines, they are never to cross. Now let's actually talk about, though, how magnetic fields arise from currents. Moving charges create magnetic fields, and a current is moving electrons. Now, for history's sake, we consider current to be positive charges moving. Obviously, we know it's actually negative charges, but here again, we are going to consider it to be positive charges moving. So whenever we're dealing with current, you're considering it to be a positive charge that is moving through the wire. Now, right-hand rule is going to give us the direction of the magnetic field, because if current flows through a wire, we're actually going to get a magnetic field that forms around it. And to figure out the direction of the magnetic field, take your right hand, point the thumb in the direction of the current, and then curl your fingers around the wire. And whenever you do that, kind of like you're grabbing it, the direction your fingers curl will end up being the direction of the magnetic field. So like in this case right here, current is flowing up the wire. So whenever we point our thumb that way and curl our fingers around, we see that our magnetic field flows this way. Now, that has some very interesting consequences if you put two parallel current carrying wires. If the current is flowing the same way, those two wires are actually going to attract. Using the right-hand rule, pointing your thumb up the wire, and then grabbing it, your fingers will curl around this direction, going on top of the wire and then behind it back here. Notice how whenever I'm trying to draw magnetic fields, let's put a B there for magnetic field. Oftentimes, whenever we're talking about magnetic fields, it will use the letter B. It curls around behind the wire. And whenever I'm having it go behind the wire, I'm making it disappear, trying to draw three-dimensional. Just because maybe you aren't the best drawer, I am definitely not the best drawer. It doesn't mean that you can't do basic three-dimensional drawings there. So whenever I'm curling around this way, and then on this side, it would go the same direction. But of interest is what's happening in between them. See, this wire on the right-hand side, the magnetic field is pointing out, coming back out at you, curling around and then coming back out at you. Where on this wire, the one on the left, it looks like it is going in. So I'm going to use circles with X's in them for in. So the wire on the right, on the side that is near the other wire, is coming out, and the wire on the left, on the side near the other wire, is going in, and opposites attract. So these two wires would end up attracting. The opposite ends up happening for these currents. If you use right-hand rule for these guys, you're going in on the inside. They're curling around and then going in. And likewise here, once again, the magnetic field going into the page. Circles with X's in them into the page, circles with dot coming out of the page. Now I have magnetic fields going the same direction, so they are going to end up repelling. If we were to zoom in maybe on this idea here a little bit better with our magnetic field lines, it would end up looking like that. Now, last thing on this slide, trying to set you up for the ones upcoming, is I've neglected to give you the unit for magnetic field strength. The unit for magnetic field strength is the Tesla or the capital T. Now, understand 1 Tesla is actually very, very large. We do not end up having magnets that are hundreds of Tesla very often. In fact, generally, 1 single Tesla is beyond what you will be well beyond what you normally experience. In fact, most standard bar magnets operate in the micro Tesla times 10 to the -6. Now, with that idea that moving charges create magnetic fields, a moving charge, whether it's a single charge that's being shot, we're going to deal with that in this equation, or it's a bunch of charges passing through a wire, aka current, moving charges basically become magnets. And if you put a magnet inside of another magnetic field or near another magnet, there's going to be a force that arises. So to calculate the force caused by a charge, Q, moving at some velocity through a magnetic field, you use this equation here. Now, angle between the charge and the direction of the magnetic field. So I want to come over here and talk about example problem 1 and 2 here briefly. This angle is 90 degrees right there. Sine theta, sine 90 degrees. So the maximum force you're going to get is whenever your charge is going, or your current is going at 90 degrees to the field. This angle here is a little bit less than 90 degrees, maybe 45 degrees. So sine 45, we're going to end up actually having less force due to it not being perpendicular. Now, here's your equation if we're dealing with current passing through a wire where I is current, L is the length of the wire in the magnetic field, and once again, angle between there. We're looking for 90 degrees to actually have maximum force. It's also worth pointing out that if your charge was going parallel to the magnetic field, or your current going parallel to the magnetic field, you would get zero force. It doesn't matter how strong the magnetic field is, or how large the charge is, or how fast you shoot it. A good show that could turn up on the IB exam is to take this equation and manipulate it into that equation. The two in-between steps that you need is the equation for current, Q divided by time, right? Change in charge divided by time, and also the equation for velocity, displacement divided by time there, and the times would end up canceling out. So you should try that as a show that. We've talked about right-hand rule for current flowing through a wire to be able to figure out the magnetic field, and the magnetic field ends up going around the wire at that point in time. But what if you put a wire or a charge inside the magnetic field? Which way would the charge experience the force? Easy way to figure that out is using the left-hand rule. Now, the left-hand rule really comes from a mathematical concept called the cross product, but we're not dealing with that right now. If you use your left hand, point your index finger in the direction of the magnetic field, so running from north to south in this example. Put your other fingers, or your middle finger, if you would like to use only one, in the direction of the current or the direction that a positive charge would flow. Positive charges are moving. Then you should be able to stick up your thumb, and that'll be the direction of the force. Obviously, if this was a negative charge, you could still use your left hand and then just flip it at the very end. Some of my students end up recognizing that to get a negative charge, you have a hand opposite your left hand that works. You just simply use your right hand for negative charges. Left hand for positive, right hand for negative. Now, we've already talked about this, but I wanted to actually write it out. A circle with an X means into the plane or into the page, and a circle with a dot is out of the plane or out of the page. Let's do a couple of example problems, actually 4 of them here. So you're going to need your left hand for all of these. You're going to be holding it up near the computer screen, and then pause the video before you end up hearing the answer. So number 1, take your left hand, point your index finger in the direction of the magnetic field. Now, rotate your wrist such that your other fingers that are pointing out 90 degrees, the other fingers are now pointing up the page, right? That's the direction of the positive charge. Stick out your thumb. The direction of the force is the direction that your thumb is pointing. That should be going into the page. Maybe we'll do a circle with an X in it. So the force that the positive charge should be experiencing in number 1 is into the page. All right, number 2, why don't you give that one a shot on your own? Just remember, it's a negative charge, so you're going to end up having to flip it in the end. All right, so take your left hand right? Or you could use your right, but I'm going to use the left and then flip it in the end. Point your index finger pointing up the page, index finger for magnetic field. Point the other fingers over going to the right. Yes, I know it is at an angle here, but we end up pointing it to the right because that's still the direction that the charge is going if we had to get the sine component, the perpendicular component of it. Stick up your thumb, and you're going to end up finding the force, in this case, is out of the page. If it was for a positive charge, right? But this one isn't. So it's also going to be into the page here because it's negative. So you go through it like it was a positive and then just change the direction in the end. Or, like I said, you can use your right hand. I mean, if you use your right hand, index finger pointing up, you're going to rotate your wrist to where your other fingers are poking to the right. Your thumb will be pointing into the page. Number three is a little bit different. It looks like I'm trying to identify in this problem whether the charge is positive or negative. I can see here from the motion of the motion of the particle that the force must be directed down the page. So let's use our left hand and let's actually align everything to see if it's positive or negative. So you're going to stick your index finger pointing out. I need to rotate my other fingers now to the right here to match the velocity. So you're pointing your index finger away from your screen, kind of right at you there. Your other fingers for velocity are pointing to the right. Stick out your thumb, and it aligns with the force right now. Left hand matches up with positive. So this must be a positive charge. If the force was pointing up here, then it would be a negative charge. Number four is similar to number three, except this does happen relatively often, this type of problem, where you need to identify the direction of the magnetic field. It looks like we have a force that goes to the right here, and I have a positive charge going forward. So go ahead and align your other fingers going up the page. Now you can rotate your wrist or elbow so that your thumb aligns with the force, and you're going to end up seeing a magnetic field coming out of the page at you. Now, something you should have noticed in all of these, let's actually put in my circles and dots for magnetic fields coming out of the page, this really should end up helping you, is that the force, the direction of the velocity, and the magnetic field are all at right angles to you. They may not occupy the same axes. In other words, check out number one. I have a charge moving in. Let's call this the y-axis for now. And I have a magnetic field moving in what we'll call the x-axis. That means that the direction of the force has to be in what we'll call the z-axis, or into or out of the page, because the y and the x were already occupied. Same thing here, right? The y and the x were already occupied. So the direction of the force must be into or out of the page. That's the only possibility here. Likewise, on this one, the force was going down. The velocity to the right, y and x are occupied. The magnetic field must be going into out of the page, in this case, into the page. And knowing that really helps you here, because you can end up narrowing it down to the magnetic field either is going to come in or out. All right, in this example problem here, we're going to pass a stream of alpha particles through some region, and in that region, they are deflected as such, kind of with a circular path. They came in with a velocity of 2.7 times 10 to the fourth meters per second, and they experienced a very, very small force, but that's actually a very large force for how small an alpha particle is. The first question, though, is state the type of fields that could actually cause alpha particles to end up being deflected to the right. Evidently, there is a force pointing towards the right. Now, alpha particles are positively charged. An alpha particle, in case you were unfamiliar, is a helium nucleus. That means they have two protons and two neutrons, so they would have a charge Q of plus 2e, or 2 times the elementary charge. The elementary charge is approximately 1.6 times 10 to the negative 19th coulombs there. Now, the mass of a proton and neutron is in the order of magnitude of about times 10 to the negative 27th. So if you're thinking about this force times 10 to the negative 15th, and F equals ma, times 10 to the negative 15th equals mass times 10 to the negative 27th here, because 2 protons and 2 neutrons. So times 10 to the negative 27th when I put 4 of them together, times 10 to the 26th, negative 26. You're still looking at a very, very large acceleration. Now, that's an aside from this problem. State the types of fields that could actually cause this alpha particle, positive charge, to end up moving that direction. Well, one of them could be an electric field, right? So if instead of if we ended up putting positive charges on this side, maybe we have a positive plate and a negative plate over here, the positive alpha particles would be attracted to the negative and repelled from the positive. So it could be an electric field. It also could be a magnetic field, to where you end up having a magnetic field that's going to go in or out of the page. Notice that the force is in what we'll call the x-axis. The initial velocity is in what we'll call the y-axis there. And so it could be caused by a magnetic field. Now, if we had actually extended this field region out to where we could see what was going to end up happening, if it had curved and then kept going kind of straight here, it had to be an electric field. If it had curved and ended up going in a circular motion, it would be a magnetic field. But that's an aside, not for this problem right now. So now let's assume that it's a magnetic field. We want to determine the maximum possible field strength, and we want to know the direction. Let's start out with direction, because that's what we just learned. So I already know the magnetic field has to go into or out of the page. So I'm going to take a little bit different approach at this problem figuring out to try to coach you on this. Use your left hand because you're dealing with a positive charge, and let's just guess that the magnetic field is coming out of the page, and let's see what happens. So I'm going to point my index finger out of the page, standing for a magnetic field coming out of the page. I'm going to rotate my wrist such that my other fingers are pointing down the page with the velocity. I'm going to stick out my thumb where the force should be going, and according to this, if the magnetic field was going out of the page, the force should be going left. Your index finger is pointing straight at you in this video. Your other fingers, middle, ring, pinky, are pointing down, and then your thumb is pointing currently the opposite direction that it should be. So it must not be, the magnetic field must not be coming down, coming out of the page or out of the screen. It must be going into the screen. And whenever you align everything, you'll notice your thumb is pointing the correct direction. Now, to figure out the magnetic field strength, we'll use F equals QVB sine theta, and we'll set theta to be 90 degrees. Now, I should say that we're not actually going to be able to look for the maximum. We're actually determining the least possible magnetic field strength, like the lowest amount. Maybe that would be a better term, lowest possible magnetic field strength that would actually apply that force. Because if I let my angle here, if I let my angle be less than 90 degrees, then I would need to up my magnetic field strength to be able to produce this same force, all the way to if sine theta was 0 degrees, then B would have to be infinity. So we're actually looking for, let's not push ourselves. What's the least magnetic field that I could put in? Because if I have the charge going in at 90 degrees, then I'll end up getting this force over here. So let's plug in what we know. We are going to know our velocity. We know our charge, 2 times 1.6, 10 to the negative 19th coulombs, and we know our force, allowing us to solve for B. Sine of 90 degrees reduces to 1, so we don't have to worry about it. And then I'm just going to divide over, and then I have my magnetic field strength. And I end up with a magnetic field strength of 0.56 Tesla, which is actually a very large magnetic field. Let's look at an example problem that deals with a railgun. Now, a railgun actually uses, if you will, 2 rails, that's where the idea comes from, and connects them in a circuit, with the projectile being the thing that completes the circuit for a very, very large current to flow. And it's that current that flows that actually creates the magnetic field that then pushes your projectile forward. Now, using right-hand rule to determine the direction of the magnetic fields here, pointing the thumb using your right hand in the direction of the current down this bar here, you would end up finding that current loops around like this. And then going back the other way, it ends up coming the opposite, which means that both of these end up having a magnetic field pointing into the plane of the paper. So yes, the bars would repel. We would need to securely fasten them. But here's the interesting part about that. This means that I have a very strong directed magnetic field in between those two bars, always going into the plane of the paper consistently. Now, I end up having a current also that is passing through this bar. In essence, if I were to kind of zoom in or if I would kind of separate that out, I have a magnetic field going into the plane of the paper, and I have current passing through like this. Left-hand rule tells me that I should end up having a force. Index finger going into the plane of the paper, your other finger standing for current, pointing down. You should end up with a very strong force pointing that way. Or, in our case, right, shooting the bar down the rails. Now in this problem, it looks like we're going after the velocity that the projectile will leave the railgun. We have a current, we have the length of the rails, we have the mass, and we have the magnetic field strength. Let's start out and let's actually solve for the force that this rail will experience. Since we're dealing with current, I'll do F equals I L B sine theta. Let's make an assumption, since the problem didn't tell us this, that the rails are separated by 1 meter just to make our life easy. So the length of the bar in this magnetic field right here is going to end up being 1 meter. Now I've got my force here. Due to this very large current, that's kiloamps. That's not a current that you will see very often. In fact, you can already start to imagine that with that large current, the number one problem that railguns have trouble with is heat there because of how much current is passing through. That does, though, produce a very, very large force. To point out how big a Tesla is, this massive current passing through doesn't even produce 1 Tesla or around those bars of a magnetic field. Now that I have my force, I can set that into F equals ma to end up calculating the acceleration. So after I found my acceleration, very large, 4/4,000, that then can go into a variable bank over here, allowing me to pick a kinematic equation to be able to solve for that final velocity. Noticing that I am missing time, let's choose the kinematic v squared u squared plus 2as. And that would end up giving me a final velocity of 318 or 320 using significant figures. Looks like my mass is my limiting one here. 320 meters per second, right at the speed of sound that this projectile would launch off with.